All right, so we're in chapter 4 on exponential and logarithmic functions, and now today we're looking at the graph of exponential functions in section 4.2. So graphing exponential functions of the form f of x equals b to the x. So how to do that? Well, first I would create a table of points, and you need to plot at least 3 points from the table to get a nice, decent graph. And with b to the x, the y-intercept is going to be 0, 1. So that's going to be your first one. And then after that, you want to try to draw at least a smooth curve through the points. Now, if you're like me, you can't draw smooth curves, but at least try to draw one. And then you're going to state the domain, the range, and a horizontal asymptote. For the simple ones, b to the x, well, our domain's always going to be negative infinity to infinity. Our range will be 0 to infinity. And our horizontal asymptote is going to be y equals 0. Okay, so when we have just that simple function, when we have b greater than 1, we're going to get a function that goes like this. Okay, so it's going to be increasing, it's growing, and it's going to be exponential growth. Now, when b is between 0 and 1, then we're going to have a decay, and so we're going to get our purple function here. So it's going to look something like that. Okay. Now, the larger B will give a steeper increase. And so, it's going to come up and it's going to be really going like this, the steeper you get. And the smallest B will give the steepest. And so it'll give you something like that. So what we're going to do is kind of go to Desmos and show you how that works. So here, let's say we have, a couple of examples we could do. We could have like for the increase, we could maybe do a 1 or a 0.2 to the x. And, it's really kind of slow. Well, what if we do 5 to the x? Well, you can see just going from 1.2 to 5, all of a sudden we got this really steep increase. And we could even do something like, maybe 25 to the x. Well, look at that. We're even steeper. And the more and more we go up and B values larger and larger, it's just going to steeper and steeper and getting closer to that vertical really right after our y-axis. Now, what happens if we have between 0 and 1? Okay, well, let's kind of change our numbers here. Let's put 0.00 or ah, 001, and maybe we can put 0.05, and maybe we can do, oops, we're just going to have to rewrite that one all together. Then we can do maybe zero point 0.6 or something like that, okay? And that's to the x. All right, uh, so here we go. The smaller they are, the 0.001, they're really, really close. Then it gets a little bigger here, and then the higher that number is, the closer to 1, it's pretty gradual. So that's kind of what we're stating here. The smallest b is given the steepest increase, so that 0.001 was right there, and then we had clear over here, maybe that was our 0.6. It was kind of much flatter. Whereas over here, maybe that was our 1, and then if we went straight up, that was our 25. So that kind of shows you how the steepness can be affected by that B. All right, so what they want us to do here is sketch the graph of 2 to the x. We want to then state the domain, the range, and the asymptote. Again, I put 3 boxes here because usually you put 3 boxes, or you need 3 points to make a nice graph. And if we do our 0, guess what? We get 0, 1, because 2 to the 0 is 1. Let's do a 1. Well, 2 to the 1 is 2. Now, those are pretty close together, so let's do one a little higher. Maybe instead of going to 2, let's do 3. Well, 2 cubed is 8. Okay, so now let's draw, or attempt to draw, I should say, our smooth curve. So 1. All right, so 0, 1. So we're going to for sure go through that point right there. 1, 2. So 1, 2, right there, and 3, 8. So 1, 2, 3, and then we have 1, 2, 3, 4, 5, 6, 7, 8. So about there. And remember, when we're coming down, it might be easier to come down. I don't know which way is going to be easiest actually. this is just going to keep getting closer and closer and closer to our x-axis. So what is our domain? Our domain is going to be from negative infinity to positive infinity, so all real numbers. That doesn't change. Now, because we're above, our range is from 0 to positive infinity. Now, it doesn't include 0 because of the next thing, our asymptote. That is y equals 0. And so this, the x-axis basically is going to be our asymptote. So we're going to get really, really close to 0, but we're not actually going to get there, okay? And so we've stated our domain, our range, our asymptote, and we've created our graph from the table. Now we could plot more points. We could plot some over here, in the negatives, and we could kind of get a better idea where it's going to be. But between 0 and 1, trying to figure out, well, is that 0.6 or is that, it's a little more difficult. So, this is a good overall graph here, and that's how I would do a graph in this case. Now, what happens is if we have a b to the x, okay? Well, remember, a is going to be our initial value. It's the 0 comma a. So that means the larger the a, the higher our intercept's going to be. And our b, remember, that was our steepness. And so the larger the b is for positives, then it's going to be, steeper. And the smaller it is for basically on the small side between 0 and 1, it's going to be steeper. So which graph or graphs have the largest value for b? All right, so we want to find the steepest one that's positive. So we look over here. Well, the positives are D, E, and F. So which one has the steepest graph? Well, it looks like D has the steepest graph. Okay, so that would be my choice for the largest value for B. Now, the smallest value B, that's going to be the one that's steepest and then kind of going down and decaying. And so if I look at the decay, I have A, B, and C, and the steepest one there is going to be C. Okay, so that would be which one I would do because it's steepest coming down. Now, those were with the b values. Again, we're looking at, b greater than 1 and then b between 0 and 1. Now with a, which is the largest value, well, that's going to be the one with the highest number here. So we go and we start here at 0 and we go to the highest one. Well, that would be the highest one. Well, that's a C. And the smallest one's going to be the one that's down the farthest. That's going to be our F. Okay. So that's how you can kind of use our A's and B's to determine largest and smallest. Now, could we determine anything between those? Yeah, we probably could and try to get them in the right order as far as, A values and as well as B values, that we could do that. And it would just take time with 6 of them. But we just wanted the extremes here to see if we could determine what the extremes were. All right. So now what can we do with exponentials? Well, we can transform them kind of like we've done before. We've done transformations. Now our base function is going to be b to the x. So that's going to be our base function. And what we can do is we can take, b to the x plus d, and that's going to give us a vertical shift. Now, our d can be either positive or negative, and that's going to basically add a constant to the parent function. We're going to move up or down. So, if our original one was like that, then if we, add, we'll go up here. And if we subtract, we'll go down here, basically. We're just going to kind of go up and down depending on where we were. We can do a horizontal shift, which means left and right, and that's going to be based on our exponent. So it's by that c. So add a constant c to the exponent part of the parent function. C again is going to be positive or negative. And so right now we're just kind of looking at all the possibilities, and then we're going to go in a little more detail as we go. So that's going to be our shift is in the exponent here is horizontal. This was our vertical shift. Now we can do a stretch or compression, and that's going to be based on our A. Okay, and we're only worried about the absolute value of that A. So if A is greater than 1, the absolute value, it's a stretch vertically. So it's going to, go from here and it's going to go up. And so it's going to be stretching vertically. And if A is less than 1, the absolute value of it, it's going to compress it. It's going to move it down on our graph here. So that's going to be our A out in front. And then one last thing are going to be reflections. So if we reflect about the x-axis, remember, That's our x-axis. So if we have something like that and we reflect across it, it's going to look something like that, and that's going to be a negative out in front, okay? And if we do it about the y-axis, so if we have this one and we reflect across the y-axis, it's going to look something like, well, sort of like that. And we have then that negative exponent, or we can have 1 over b to the x if you want to look at it that way. But it's going to have a negative to the power here, okay? And so then we're reflecting it across that y-axis. So those are the things we'll see, kind of like we've seen before. You know, we have the 4 different things before. And so what we're going to do now is kind of work our way through those and see them in a little bit more detail. So let's start with shifts vertically and horizontally. So, you know, that's going to be our plus c here and our plus d here. So shifting parent functions d units vertically with the same sign as d. So if d is positive, we move up. If d is negative, we move down. So that's a negative d, that's a positive d, and we'll put d, I guess, there. Okay. So that's how that's going to work. We're just going to up or down. And then it's going to shift parent function c units horizontally with the opposite sign of c. So if we have plus c, what's going to happen there? Well, we're going to go left. And if we have a negative c, we're going to go right. So that's kind of one of those tricky things we've seen before. So that's nothing new. Now our y-intercept is going to be b to the c plus d. So that's something kind of different there. And our horizontal asymptote is going to be y equals d. Our range will be from d to infinity. So, you know, we're shifting up or down. So that's going to be our new range part. And domain, guess what? It stays the same. So it doesn't change. So let's look at some here where we're doing our shifts horizontally. So we're looking at the exponent part. So our 2 to the x, you know, we have our normal thing going up, and that's going through the 0, 1, and it comes up here, and that's what it looks like. Now, if we go and look at a plus 3, well, plus 3 says we're going to shift it left. So we're going to go basically, you know, 3 uh, that way. So we're going to go here, and that's going to give us 1, 2, 3. And so that's going to be shifting that unit 3. And then if we move around 3 units, it's always going to move it 3. Now here we have minus 3, so that means we're going to go right 3. So now we're going to go, you know, 1, 2, 3. So that'd be 3 units right. And however we do it, it's going to go 3 spaces to the right for our horizontal shifts. Now if we do vertical, you know, we're going to go up or down by the d. So if we go plus 3, guess what? We just go up 3 units. Now guess what here? Notice this one, the horizontal uh, asymptote didn't change. It's always y equals 0 when we only are doing horizontal shifts. But when we start doing the vertical shifts, our horizontal asymptote changes. It changes to y equals 3 in this case. Now this is our original y equals 2 to the x. And then when we go down 3, well, we shift down 3, and now our horizontal asymptote is a negative 3, okay? And so our range changes on these, doesn't change on these. The only thing changes here basically is where we're actually hitting the vertical asymptote. But here, what happens is now our range is from 3 to infinity. Here it was from 0 to infinity. And here is from negative 3 to infinity. So those are the kinds of things you'll see with vertical and horizontal shifts. All right, so let's pause there and we'll come back for more.